Today let's discuss how to use the inverted index for query processing. So let's go back to our example query where we had Brutus and Caesar and not Calpurnia. Now the query has two terms here, let's say Brutus and Caesar. So let's first see how to handle the and part of this query. So let me get my pen on. Okay. So we are interested in Brutus and we are interested in doing an and between the terms Brutus and Caesar. So first we have to locate Brutus in our dictionary. Then we have to retrieve the postings of Brutus. Instead of calling it a postings list, sometimes I may take a shorthand of calling it as postings. They mean the same. Um, and then we locate Caesar and retrieve its postings. So I have the postings of Brutus here, and I have the postings of Caesar over here. And now I have to do an AND operation to figure out the documents that contain both Brutus and Caesar. So this could be a good moment to pause the video. And if these are the lists given to you, so these are the document IDs. So document ID 2, document ID 4, document ID 8, and so on contain the word Brutus. If document ID 1, document ID 2, document ID 3, and so on contain Caesar, can you figure out which are those documents that contain both Brutus and Caesar? Just pause this video for a minute and work this out for yourself. Okay, so let's solve it. So we see that Brutus appears in 2, Caesar also appears in 2. So document ID 2 is in our results. So let's figure out the results set. So Brutus appears in 4, but there's no 4 here. So Caesar does not appear in 4, so we're not interested in this. But we see that document ID 8 contains both the terms. Is there anything more? I don't see any. So these two form our results. So this process of going through the postings to figure out the intersecting document sets is what we call as merging the postings. So we retrieve the postings for the terms of interest. So we retrieve Brutus postings, we retrieve the postings of Caesar, and then we merge them to figure out the results for the AND query Brutus and Caesar. Now intersecting two sorted linked lists. So remember these linked lists are sorted. The way we created it, there was a step sorting step there. So these can be assumed to be sorted. Now, if you have sorted linked lists, how would you do the merge? So this is a very common interview question. You could go and look it up on a variety of websites. All top companies seem to have asked this in some or the other interview. Now it turns out that the merging is pretty easy and straightforward. There's a clever way of doing this in an order of m plus n operation. How would you do that? You use two pointers. So let's say I have a pointer 1 and I have a pointer 2. So initially I set up these pointers at the beginning of the postings, and then I compare the values where these pointers are pointing to. So let's say this is P1, let's say this is pointer P2. So 1 and 2 are not the same, but 1 is lesser than 2. So I increment this pointer. So now this pointer is not here. So this pointer moves here. Now I compare these two. Yes, now there is a match. So I return the match. So let's say my return is a set. So that I don't need the, just a second. All right, sorry about that. So we have 2 in our result. And now that I have a match, I continue to increment. So now I go here. Now we see that 3 does not match and 3 is larger than 2. So now this time I increment this pointer. So now P1 again does not match, but P1 is bigger than P2. So let's increment this pointer. So likewise, these pointers go from left to right till the end of the list. and wherever there is a match, I just spit out the match, and thus I construct the merge results. Now you can see that if the first list has m items in it and the second list has n items in it, so in an order of m plus n operations, I can complete the traversal and get all the intersecting items. Since it has linear complexity, we like these kind of algorithms. For those who are new to the world of algorithms, we hate algorithms which have quadratic complexity, order of n square, or n power n, 2 power n. So these are considered to be very fast growing functions which we don't like. Anything which is linear or sublinear is usually considered to be acceptable. Well, of course, we always ask questions as to, can we improve this even further? So now we have a linear solution. Can we look for sublinear solutions? Usually, the tree data structures provide interesting sublinear data structures, but for now we'll not get into them. So we are happy with having a postings list and merging them in linear fashion. Okay, so now the big picture has changed a little bit more. So remember, we started by building a term document incidence matrix. We said that this is much better than opening the files, and then we have now graduated to building an inverted index and then using that for content for matching, right? So the content, which is a set of documents, have graduated from the format of being documents to term document matrix and now to inverted index. And the query handling has moved from matching the words in each file to taking the matrix rows and doing an AND operation on the rows to intersecting the postings list. So we have done some progress on. So we now have a system which is slightly better than our previous system. So the big picture has changed from working on a collection of documents to working with an index, with an inverted index, and doing a merge. All right. Now, can we do even better? We already have a linear algorithm to merge. Can we do this matching process in even more effective way? So it turns out that yes, it is possible. This idea is inspired from the multi-level indexing idea of databases. So we introduce what is called as skipless. So we could have some additional pointers in our linked list. So the Brutus linked list, the postings of Brutus was simply a list of all the document IDs, and we used to navigate from left to right. But we could have additional pointers which could jump and take us to some value which comes down the line in the list. So if you look at this, so I have two pointers from 2, one which goes to 4 and one which goes to 16, and from 16 again one which goes to 28 and one which goes to 19. So this one is a sequential pointer, and this jumps at an interval of 3, right? So for every fourth element, or 3 elements after this element, I can jump if I want to. Similarly, the Caesar skip list looks something like this. So I can jump to 5, 51, and so on if I want to. And of course, the last element can either be null, or I can simply put the largest a number which is larger than the largest document ID that I have, so that I can stop there. The advantages of the having a skip list is that you can still use the 2-pointer approach to merge them, and when you start looking at the list, you can also use, so for example, in this case I know that the next one, I have 5 in this list at some point of place, so I don't want to take the 16 pointer, so I rather want to go sequentially over here. But if I have a very large value, I can choose to just skip. I hope the idea is clear to you. So for example, Now in this case, I am at 1, 1 is less than 2, so I would like to increment this pointer. Now I go here. So why do I take the sequential pointer, and why I don't take the root of 5? Because 5 is much larger than 2, and I hope to see 2 somewhere between in this list between 1 and 5, right? So that's why I chose to take this pointer, right? So it's up to us to decide which one to take. So the algorithm goes like this. So now 2 and 2 match, so I return the result 2, and then I increment. So there is no option here, I have to go sequentially. There I cannot jump, so I go here. Now 2 is less than 3, so now I have to choose either to go to 16 or to go to 4. Now if I had seen a number which is more than 16 over here, then I would have taken this route to jump to 16. But since the number is only 3, which is much lesser than 16, so I go this way. So I land on 4, right? So once I land on 4, I compare 3 and 4, they're not the same, so I increment this pointer and I reach to 5. They don't match, but 4 is lesser, so let's increment this. So I now compare 8 and 5, they don't match. Now I have a choice here. So either I can go to 8 or I can go to 51. Obviously I will not like to go to 51 because 51 is much bigger than 8. So I take this pointer over here and I reach to 8. There is a match, so I retrieve 8, and so on. So so when we encounter larger numbers in the list, these skip pointers become useful, and that way I can save some comparisons. Thereby I can achieve even better merging efficiency than a linear merging efficiency of order of m plus n. um, as I said, the advantages are that it achieves sublinear intersection time even better than m plus n. It works better for a static index. So what is a static index? So far we have been assuming that index never changes, um, and it just stays like this. So if you create all these additional pointers, you don't need to worry about the overhead of updating these pointers when the list changes. So let's say every month you go and crawl the web, get the documents, construct the index, and leave it there. If that is the case, then skip lists are fine. But if you don't want to crawl the entire web and replace the entire index, but you want to incrementally go grab something and update the index, then you have to be very careful in updating these skip lists also, and the updation of skip lists is going to be painful and it's going to be expensive. um, this is useful for AND query. Can you think of a case of an OR query? What happens if I have Brutus or Caesar? Would this be useful? What would you do in that case? Well, if I have to resolve Brutus or Caesar, I would simply take all the items in Brutus and union it with all the items in Caesar. So that will be my result set, right? So instead of 2 comma 8, it will be 1 2 3 4 5 8. So this is basically the union of everything here with everything over here. So in this case I really don't need a skip list at all. Yeah, so that's why it's not useful for a OR query. Are there disadvantages? Yes, we need more space to store the skip pointers. The effectiveness depends on where we place the skips. So how do we know that every fourth item should have a skip? Why not every fifth item? Why not every 10th item? How do we know what kind of gap is good? So this is a complicated problem. Research shows that root n, where n is the length of the list, root n is one of the good measures of having the skip gap as, but there is nothing which um, uh, so it could be data dependent, and it could be query dependent as to what the users are likely to query. um, the more skips you place, the shorter will become the skip interval. Therefore, you have to make more comparisons. And the whole point of doing the skip list is to reduce the number of comparisons. So we would not like to have more skips. But if you make lesser skips, then you use less extra space. So lesser number of pointers are added to your list. But then you'll have to do more linear comparison in that case. So we have a trade-off here, and finding the right trade-off could be very tricky. Here is another example or a variant of skipless where we have multi-level skips. There's no need that you have only one level of skips. So I can have another pointer here jumping directly to here, right? So similarly, a pointer jumping directly to here. So this is 55 and 51. So I have 6 and 28. Now, why would I, or how would this be useful? Why would I do this? The reason is, if I know that the one which I'm comparing to with is already, let's say, 40. So this is, let's say, 40. I'm comparing with 2. So there's no point in going through all these numbers sequentially. I take the 28 route and directly jump into 28 and start comparing from here, right? So multi-level pointers make the search even faster, but it also comes with the cost that you have to store now even more pointers. So there is a space overhead involved over here. So what's happening in this example? Um, so start with the head. So it's pointing. So this is the sequential pointer going through my postings. I use nil to represent the last element, and from the first pointer I also go to the third pointer. So I have a skip pointer over here, um, and from 4 I go to 6, from 6 I go to 9, and so on. So there's another one going from 1 to 4, and there's another one going from 1 to the end of the list as well. So I can implement a multi-level skip to help me do a faster traversal. Lucene is a search platform framework which allows you to build search engines. We'll see a demo of this later in the class. And Lucene already implements all these kind of ideas like multi-level skip list. So it's just a matter of using it. So that's why knowing all these things is important to us. So as I said, there is a multi-level skip list writer class in Lucene. All you have to know is how to configure, how to pass these values, how to set up the skips, and how to call them. So it's that easy. You don't have to re-implement all these things yourself. Okay, now let's go ahead and discuss phrasal queries. What if I am not interested in independent words like triple IT, Sri, and city, but I am interested in the entire phrase triple IT, Sri, city. So I want to see whether the entire phrase exists or the phrase doesn't exist. I'm not interested in the words. Then what do I do? Right. So if you look at this, I do not want to match triple IT Delhi, even if triple IT exists in triple IT Delhi. So far we have been looking at and or and not applied to terms. So I would say, let's say triple IT and Delhi, right? So that would give me a phrase match, and not triple IT or Delhi, which will give me a word match, right? So is there a better way of dealing with phrasal queries? People have discussed different ways of doing this. One idea is a pretty simple idea, which says just index all the bywords. What do you mean by bywords? So after tokenizing and removing the stop words or the words which we are not interested in, what we could create a combination of two words that appear in sequence. So in this case, friends Romans and Romans countrymen, right? So there are two byword phrases. So this entire thing is called a bigram or a byword. And so I can take these kind of byword sequences and then index them. So if I go back to my index, yeah, here, so we no more have single words, but we have bywords. So ambitious b Brutus, Brutus capital, capital Caesar, capital ambitious. So all kinds of bywords that are possible get into my dictionary. Very quickly you would have noticed that this is not a good idea, because our dictionary is going to bloat up like anything, right? So all possible two combinations are going to be huge. So we don't like this idea. Can we do better? Let me go back to the slide. Yeah. Um, okay, so let's take another example. Triple IT Sri City Chittur. Okay, so this is the query that I have and I want to match. What one thing I could do to improve efficiency is, instead of going word by word and putting an OR query, I could do complete AND query, but then that might not be a good idea either, because the words might be spread across and there could be something in between these words appearing in the documents. So I can choose to use a byword index then. So in which case I need to have triple IT Sri and Sri City and City Chittur. But even that has a problem. Um, we don't know if there is something, so if the document might not have city Chittur in it, it might have city and then triple IT Sri City in Chittur or something like that, in which case this will not match. Okay, so can we come up with something interesting here to ensure that these kind of phrasal queries can be handled better in even more sensible ways? So natural language processing techniques come here for help in query formulation and matching. So let's take an example. So we could store the index in this format, where I have the term to be indexed, the number of documents containing the term. So this is basically a representation of my dictionary. So remember, I had ambitious. Sorry about that line there. It's a glitch in PowerPoint. So I have ambitious, and the number of documents, it appeared in one document, and in doc one it appeared in, let's say, fourth position or something like that, right? So I can have the positions listed out here. So if there is another word which appeared in multiple documents, I just list all the documents and the positions. Let's look at an example. um, So let's say I have two words, to and be. These are the words, and it appears, the word to appears 993k times in my collection. Let's say, so it's a frequently appearing word, looks like. And similarly, be appears 178k times in my corpus or my collection. Okay, and then what do I do? So I list the doc ID. So each one here is the document ID. So I have document ID 1, I have document ID 2, document ID 4. And in document ID 1, the word to appears 6 times, and it appears in these positions: the 7th position, the 18th position, the 33rd position, and so on. Yeah. Similarly, the word to appears in document 2 5 number of times, and it appears at the first position, 17th position, and so on. So likewise, these are the documents that contain the word to, and similarly these are the documents that contain the word be. Okay, so this is one way to create an index. We call this as the positional index. Okay, so let's say a positional index like this is given to you. Can you tell me which documents are likely to contain the phrase to be? Right, so the phrase to be. Can you look at this? And so this is a good time to pause the video for a minute and calculate which are the documents that are likely to contain to be. Okay, let's work it out. Um, for two and for B to appear after two, the position should be um, immediately next to this, right? So for instance, 2 happens at 17th position, then I expect B to happen at 19th position, or the immediate 18th position, depending on how I index how I index the positions, right? So now let's assume that um, we have sequential. We are looking for sequential entries. Okay, so look at this. In the fourth document at 190th position, we have 2, and in the fourth same document at 191st position, I have B. So that means document 4. Um, so this is the first position, second position, and so on. The 190th word in document 4 is 2, and the 191st word is B. So doc 4 is likely to have to be here. Are there any more documents which could contain? If you look at it carefully, document 4 seems to have to be at 429 and 430th position as well. So it appears twice, so later as well, right? So this is at 190th position. So is there any other document? So since B appears only in 3 documents, 1, 4, and 5, we are interested in looking at 1, 4, and 5 only. So we have already seen 4. So let's take a look at 5. What about 5? 363 and 367. No, there's no B after that. So 5 is not a candidate. What about 1? We have 18 and 17. So this is like the inverted version, right? So B comes first and then 2 comes. So we are not interested in this combination. So we don't seem to have any other good match. So it's the answer seems to be doc 4. Okay. All right. So the doc 4, it seems to be appears one more time. So we have 433 and 434 as well. So somewhere down the line at 433rd position, we have another 2B. Okay, so given a positional index like this, phrasal queries can be even more effectively conducted, right? So because we now have the positional information of each term. So that's the beauty of constructing an index this way. So the only thing that we have done here, so we already had the word, we already had the count, and we already had the list of document IDs, right? So this is something which we already had in our inverted index. Now along with the list, we are storing the positions as well. That's the only additional information I store, and through that I get the benefit of answering phrasal queries better. This also allows me to do proximity search. So I can say "it slash 3 Chittur," where slash 3 means that within 3 words of "it" I want to see Chittur, right? Again, if a positional index like this is given to you, these kind of queries can be worked out. The problem with positional index is that merging the postings requires you to do a lot more calculations, so it is expensive. So in some cases where the phrases are extremely popular, we still go ahead and consider the option of adding them as a single item in our index, right? So when we created the inverted index, in the normal inverted index, not the positional one, we may include some bywords or try words and so on, if provided that there are lots of queries and we don't want to do this positional computation every time. Okay, so the moral of the story so far is that all these index formats can be combined to leverage the advantages of each other, especially byword and positional index ideas can be combined. They can be used to answer phrasal and proximity search queries. And in some cases, we may still use the byword index and add bywords to the index, provided the phrases are really popular. And we use positional index in cases where we we expect things to get interleaved, uh, so that a byword match will not happen. Let me now revise the different index types that exist. Um, the lame way to um, do the search would be to use a forward index. A forward index is a straightforward index where you remember all the words that exist in a document, right? So document is made up of a set of words. That's one of our assumptions in the Boolean query model. So let's say document 12 has these words. Mary has a little lamb. Document 13 has the wolf ate the lamb, and so on, right? So this is simple forward index. Um, I can use this forward index to kind of so let's say if the query is lamb, right? So what would I do? So if the query is lamb, I have to go to document 12 and see whether lamb exists, and then I have to go to document 13 and see if the lamb exists, and so on. What is the advantage or disadvantage of this? So let's say there is an update to document 13, and the new version of document 13 has today the wolf ate the lamb. All I have to go and do is simply come to document 13 and add the word today to the set of words that I already know for document 13, right? That's all there is to do there. And then I would just process query, just as I told you. I have to go to each document and do it. I don't like this idea of going through each document ID and then comparing. So it would be something like this. So I start with each document ID, go to its list of words and see whether the list of words is of interest to me. If you want to do phrasal queries or positional queries, obviously you need to remember the positions as well. So Mary appeared at position 0 and so on. So we had to keep the location ID information as well. So this is an example of a forward index with positional informations. So in this case, let's say the query is little lamb, then I go to each document and look for little first and then see if the immediate next word is lamb. I can use this using the positional information or some pointers going from one to other. So this kind of index is called a forward index, and quite clearly this is inefficient, because assume you are in a web scale where Google has million documents and there is a query. So you have to go from top to bottom across all the million documents and then conduct your normal query or phrasal query. So this is the reason why we like the inverted index. So what did we do in the inverted index? Um, for every So we have term wise organization. So for every term that we expect user to query, I have the list of documents that contain them. So this is already processed and kept. So when the query comes, if this is ordered, if the dictionary is ordered, usually the dictionaries are ordered. You are used to your regular dictionaries, right? So you could do efficient ways of searching. So let's say you do a binary search, so you don't have to go linearly searching for the term in a dictionary. And once you have the dictionary term, then you know which documents have it. So it's a lot faster way to respond to a query. We could use an inverted positional index. So we took the to be example. and I told you how to navigate through this positional index and compute that document 4 is a match for 2b. So these is a really smart structure for phrasal or positional queries, but the problem here is that we are storing more information, so obviously your index is going to consume more space. This is how your inverted positional index usually looks like. So let's say I have some documents. The old night keeper keeps the keep in the town and so on. So let's say we have a lot of documents like these, and I want to index. So I simply give it to Lucene, and Lucene can create an inverted positional index for me. So let's see what happens. So I have a word, and the word appears in document 6 in position 1 and position 6, it seems. So we have document 6 position 1 and position 1 2 3 4 5 6. So this is 1 and the 6th position. So that's what I say here. So in document 6 I have and appearing at the first and the 6th position. So likewise I can go ahead and store this as a table with all the positional information. Now you give me any phrasal or positional or proximity query, I can respond to that query by looking at this table. There is yet another type of index called the Permutation index. Um, Consider this example. Let's assume the term in our dictionary is hello, and we just rotate this term. Uh, First of all, we want to know that O comes at the end, so I add a dollar at the end. For now, let's assume our queries don't are not case sensitive. So let's say I convert it to a lowercase and put a dollar at the end, and then I keep rotating letter by letter. So I have yellow dollar, and then H moves at the end, and then E goes to the end, then L goes to the end, and so on. So I have hello rotated in all possible ways and stored. But why would I do this, right? So the thing is, let's say I do the exact same thing as inverted positional index, but for every word I also have the rotated version of the word. So and dollar, right? ND dollar A, and so on. So for all possible rotations uh, with a dollar symbol included to mark the end of the word, I keep the permutations as well. So since we are permitting the term and storing them also in the index, we call this as a permutum index. But why would I do this? Can you think of a use case where such a permutum index will be useful? Maybe a good time to pause the video and think. Sometimes our brain is brilliant and sometimes it just refuses to work, isn't it? Let's go and look at it. Usually this is used when I have a wildcard query. So what do you mean by a wildcard query? So let's say the user wants HE star, um, just HE star or HE star O. Okay, so I want to match all those documents which contain words which start with HE and end with O and any character in between. Okay, so if these are the kind of queries that I want to match, what I could do is I could rotate this as well, keep the star at the beginning, add a dollar at the end, and now rotate. So we have star 0, star O, sorry, and then I have a dollar, right? And then just take this HE this side. Now this will match with one of the permutations where the prefix is this, right? So that would be the immediate next permutation to this. I haven't written it over here, so I have O dollar HELL, which is the next permutation here. And now what happens is that I take the first these four characters and try to match as a prefix, and if it matches, then I return all those words where that matters. So hello matches, so I return hello as well. Isn't this a smart way to handle wildcard queries? So this is another example of what we could do with the inverted indices. We also have a Kgram index, where so remember, K-word index is different from a K-gram index. In the K-word index that we saw before, we used the example of Taj Mahal, where there were two words being stored together. Now we are talking about characters within the same word. Okay, so that's what a K-gram index is. Say April is the cruelest month is an example sentence. What are all the bigrams that you get over here? So if the start and the end are marked with dollar for each word, so then I have dollar A, and then I have AP, and then I have PR, RI, IL, and L dollar. Yeah, so these are all the bigrams that I can expect from April. Why do I use the delimiter dollar at the beginning and the end? Because it's useful to know what makes a word, and that way I don't match with any other AP. So I know the words. Let's say I'm interested in the words which start with AP. There is a way to do that now if I use a dollar. Okay, so I can rewrite this entire sentence like this, and I can store this as an index, and then do a search. So if you give me cruel, then I'll search for $C, CR, and so on, and whichever matches, I'll try to return that to you. So here is a snapshot of such a index. There will be ETR, for instance. It matches. So this is a 3-gram index. It matches with all these words, right? So there is ETR somewhere in all these words. Yeah. So if you give a partial query or a wildcard query, another way to answer this would be through the Kgram index. So I can do an AND or kind of combination of Kgram index to return the same result. Again, there is a lot of space getting consumed to store additional Kgrams, but it probably is a little simpler instead of storing the positions. So how does the bigram inverted non-positional index look like? So remember, we could combine different ideas and have a composite index. So here I am giving you a collection with two documents, let's say D1 and D2. So if D1 is India and D2 is Asia, how does the bigram inverted non-positional index going to look like for this? Good time to pause a video and work it out for yourself. So thanks for watching this lecture, and hope to catch you with more in the next one. Thank you. Bye-bye.